Okay, maybe we can get started. So it's a pleasure to introduce Thomas Mertens, who's going to tell us about lower dimensional gravity.
Okay, so thank you. Let me first thank the organizers as well for organizing this conference and for inviting me. So my talk will be roughly based on two different, it will be divided in two different parts, which will be disconnected roughly. And the first part will be about classical JT models for black hole evaporation, in particular charged black hole evaporation, which is based on a paper that appeared on the archive last week. And then the second part will be about a topic that I've been thinking about for the past 4 years or so, about lower dimensional gravity as gauge theory and its subtleties, based on these two papers and also ongoing discussions. Okay, so let me get started with the first part, which is classical JT models for black hole evaporation. So first, a quick review. So the JT gravity action on a manifold with a holographic boundary has this form, as everyone knows. And well, the dynamics of JT gravity, as has been shown 6 years ago, is governed by a Schwarzschild action on the holographic boundary. And here I write the Schwarzschild action. This coupling coefficient big C, the Schwarzschild coupling coefficient, is inversely proportional to the 2D Newton's constant that appeared here. And well, just for completeness, I write down the Schwarzschild derivative there. And what this tells you is that JT gravity is a theory of frames, because f of t here is a dynamically evolving Poincare time coordinate, big F, in terms of a preferred time coordinate, small t. So those are the degrees of freedom of JT gravity. Now, if we add a 2D CFT matter action, matter sector in the bulk that couples to this boundary time reparametrization, the equation of motion of the total system, the gravitational equation of motion, is essentially just energy conservation. And well, this is what it looks like. It's the E dt, where E as a function of t is the total energy of the system at some time t, which is given by also just a Schwarzschild derivative. And this change in total energy in our system is equal to the net influx of matter coming in through the holographic boundary. So TVV minus TUU, so I've introduced light cone coordinates here. U and V are these light cone combinations, such that, well, this difference, TVV minus TUU, evaluated at the holographic boundary, is the net matter influx coming into our system. So this is just energy conservation. Now, if we have quantum matter instead of classical matter sourcing our gravitational model, then we would just replace these stress tensors by their quantum expectation values. And this equation is then just the JT version of the sourced Einstein equations sourced by quantum matter. So now let's apply this equation to the specific setup of black hole formation and evaporation. So we send in a matter pulse of an energy A0 at some time t equals 0 in the matter Poincare vacuum. And we then implement absorbing boundary conditions at our holographic boundary to model first black hole formation by sending in this pulse, and subsequent evaporation by allowing the radiation to leak from the holographic boundary. So this is a calculation, of course, that has been done many times during the past couple of years. So this is the energy pulse. And then the holographic boundary here is absorbent. Now let's impose the boundary conditions to implement this absorption. And well, the interesting one is this one, TVV. So TVV is the infalling component of the matter stress tensor, and TUU is the outgoing one, the one that's going towards the holographic boundary. And to implement absorption, we will choose the observer on the boundary line, so the observer that's moving on this holographic boundary, to remove all Hawking radiation he detects in his local frame. So his detector is calibrated with respect to his vacuum, and he says that there's no Hawking radiation that's being reflected back inwards. So that means that TVV is set to 0. This TVV is set to 0. So our equation reduces to this. So what is TUU? Well, this outgoing component TUU is just a standard Unruh type of calculation. So let me sketch briefly how it goes for a massless scalar field. So, well, the C equals 1 matter sector, where TUU is just du phi du phi. Now, as a composite operator in the matter quantum theory, this object requires regularization and renormalization. So that's what I write here. So well, as a standard, we point split this object and we subtract its divergence from it. And if we then evaluate this in the Poincare vacuum, for which this first piece looks like this, where this F is this boundary dynamical frame again, well, then you can just series expand this thing and you see that the first pole cancels out. And this constant term in the U1 to U2 expansion is the thing that survives. And in the end, you obtain that the matter piece TUU, the matter stress tensor, is just given by a Schwarzschild derivative as well of the frame with respect to the coordinate u. Of course, you can find this directly just from the conformal anomaly or the anomalous transformation of stress tensor components into the CFTs, but this was just an explicit example. So if you do that for a generic matter CFT, this is the source equation you get. ddt of the total energy, and the total energy, as I mentioned, was proportional to Schwarzschild derivative, is equal to minus the matter TU at the boundary, but that was also a Schwarzschild derivative. So we plug that in here, and this is the equation we need to solve. Now, in terms of the energy, this is just saying that the EDT is proportional to minus the energy. So the total energy in our system is just decaying, is dissipating exponentially after an initial injection E0. So that's the energy profile as has been studied in quite a few papers over the past few years. Okay, so now let's come to the new part and let's try to generalize this to a charged system. So instead of just starting with the Schwarzschild model as our boundary description, now we add the second piece here as well. For a new field, sigma of t next to the reparametrization f of t. And the sigma of t field represents a preferred gauge transformation at the boundary that is again becoming physical, just like for the reparametrization f of t. This is a coordinate transformation in the bulk, but it's becoming physical at the boundary. So this is precisely the same logic extended to a gauge transformation next to the coordinate transformations that f of t represents. And the second term is also precisely the boundary action of a bulk modeled U1BF gauge theory model. Now, why do we write this specific model? Well, you can get an action of this type from several perspectives. First of all, it describes the low energy dynamics of a charged SYK model. So it's governed by this, well, essentially the sum of these two actions indeed. And then secondly, it also describes the near horizon, near extremal dynamics of a charged black hole in higher dimensions, but in this case, including the charge fluctuations, which are then described by this gauge mode sigma next to f of t, which is governing the metric fluctuations. And in that case, if you come from this higher dimensional perspective, these coupling coefficients of the Schwarzschild model big C and the one for this gauge piece big K, they would be related to the extremal parameters of the higher dimensional black hole. But that is not the perspective that I want to pursue here. I just want to start with this model and try to do the same thing, send in a pulse, form a black hole, a charged black hole in this case, and then allow it to evaporate by implementing absorbing boundary conditions. So when coupling this gravity model of the previous slide to a generic charged matter CFT that is going to allow the black hole to evaporate, the resulting equations of motion for F and sigma, in this case, are energy plus charge conservation. And this is the result. These are the two equations of motion. So the first one is the energy conservation and the second one is the charge conservation. So let me go in a bit more detail. So in the energy conservation, there's this minus C Schwarzschild derivative again. That's the same energy we had before. Previously, this was the total energy. Now it's just a piece of the energy. I will call this the black hole energy. And then there's a second term, K over 2 sigma prime squared. And this is the energy that's contained in this additional charge sector. And this would be the energy contained in the exterior electric field if we were to come from a higher dimensional black hole. And then K sigma prime is the total charge in the system. And well, the first one is energy conservation as a response to net energy injections from the matter sector at the boundary. And on the right-hand side of the second equation is the net charge injection from the holographic boundary. So again, this is the JT version of, in this case, the coupled Einstein-Maxwell system, where we treat the metric degrees of freedom and the gauge field classically, but they're sourced by quantum matter, in this case, charged quantum matter, charged CFT quantum matter. Okay, so now let's try to do our same setup. We send in a pulse, in this case a charge pulse with an energy E0 and a charge Q0 to form a black hole and then allow it to dissipate by implementing absorbing boundary conditions. So what are our boundary conditions on our matter fluxes? Well, to implement absorption, we again impose that there's no reflected energy and charge at the holographic boundary. So next to TVV being 0, we also say that JV has to be 0. And then we just compute the other component, again, using the standard Unruh type of calculation. So, well, I'll briefly go through the JU component. And again, for concreteness, I will discuss the simplest matter sector one can imagine, a complex massless scalar field phi with a charge Q. It has a conserved current, and the JU component is written like this. Again, this is a composite operator, requires regularization, renormalization, and so on. So you define it like that. Then you evaluate it in the Poincare vacuum. You get an expression like that. You Taylor expand, and then you find the contribution, the renormalized contribution to this matter flux, which is essentially proportional to sigma prime. Now, given this value of the quantum Ju, you can insert it in the charge conservation equation. So K sigma double dot, so this is the time derivative of the total charge in our system, is equal to minus this Ju value plus then the percent with our pulse. And again, this is solved by an exponentially decaying profile after an initial jump from the injected charge. So the charge dissipates exponentially from our system. Then we need to look at the energy conservation equation. So again, TUU, I write the expression like this. Again, for a massless charge scalar field, you go through the same analysis. You find that it has two terms in this case. It has one proportion to Schwarzschild derivative and one proportion to sigma prime squared. We plug that in the energy conservation equation, which looks like that. And now we use that we already know what sigma of sigma prime of t is, because that was a total charge in our system. And then we find the explicit answer. So this is not very hard to do. And the explicit solution for just the black hole energy, so just the minus c Schwarzschild derivative, is that it's a sum of two decaying exponentials. Well, the details don't matter, but I just want to show you, one can just solve it. Yes. Well, you can see it in the exponent. So this one has a q squared over k. So this is the one coming from the charge sector. And this one has the big C here, which was the one coming from the Schwarzschild sector. Okay, now there is a small puzzle here with this exponentials. Try to plot it. Which is that, well, it doesn't necessarily have to be a sum, it can be a difference, depending on the sign, of course, of the relative coefficients. And what I've drawn here is just the black hole energy from the previous slide, so minus c Schwarzschild derivative as a function of time. So it's 0 for t less than 0 because, well, there's nothing there. Then there's a jump because of the pulse, and then it decays. And the blue one is the one if you have zero charge injection, so it just decays monotonically. But if we shoot in, or if we use larger values of Q0, you can see that the black hole energy, if Q0 increases, can actually increase at early times before dissipating, like the green curve is doing here, for instance, or the red curve just a little bit here. So what is going on here? So to get a little bit of intuition into this, consider just the thermal Hawking-Unruh heat bath density in 1+1 dimensions. So this is the precise formula. And let's look at the zero temperature case of this formula to see more clearly what is going on. So if we take the zero temperature case of this charged Hawking-Unruh heat bath, you find this thing. And unlike the uncharged case, for which the zero temperature limit gives nothing, in this case, there is still an occupation in the heat bath of these superradiant modes, to use the same word as in the rotating case, which are low frequency modes in the heat bath, where omega is less than q times mu, and mu is the electric potential of the black hole. So they are still there, and they would cause this zero temperature or extremal black hole to emit superradiant radiation and then heat up. And then once it heats up, after a while, ordinary thermal Hawking radiation takes over, and then it dissipates entirely. So that is what is going on here in these types of plots. So there's superradiant emission going on in the initial phase, and then the usual thermal emission takes over in the end, and everything dissipates completely. Also, as a sort of sanity check, I note that the total energy in the system, not just the black hole energy, but the black hole energy plus the one in the electric field, that always decays monotonically, as you would expect. And well, to show that what we have found here is actually the right answer, it's interesting to note that we can embed this in a supersymmetric setting. And well, to see that, note that our equation of motion in the uncharged case had a very nice, structurally a very nice form. Its ddt of Schwarzschild derivative is proportional to a Schwarzschild derivative. So there's a very natural analogous equation you could try to write down for a supersymmetric model, which is you would just write down the superspace equation, ddt of a super Schwarzschild proportional to the super Schwarzschild. And then if you would try to, if you would write this out in component equations, you would get a set of coupled differential equations like that. So the first one is just energy conservation. Then you have charge conservation for each of the number of charges there are, in this case, in this, R symmetry group of the superalgebra. And then you have a dissipative equation for the fermions as well. And you can analyze the system a little bit. So some of the properties are, you can consistently turn these fermions off as long as you don't send any supercharge system to begin with, which is something you physically don't really want to do. the charges again all decay exponentially in this case, and then the black hole energy, again, it can increase at early times if the charge injection is sufficiently high. So you get exactly the same kind of conclusions as before. And indeed, if you apply this now specifically to n equals 2, where the R-symmetry group is just U1, you precisely reproduce these charge dissipative equations I had on the previous slides, but then of course with a specific relation between the coupling coefficient of the charge and the gravity sector as dictated by supersymmetry. So there's a natural supersymmetric embedding that sort of shows us that we did the right thing. And finally, let me show you, well, the page curves you would get from this setup. So I've just shown you how the energy profile looks like. So you can also compute the entanglement entropy. So here I have 4 plots. This X essentially is proportional to the charge injection. So this is from, let's say, almost no charge injection with the pulse to maximal charge injection with the pulse. And these kinds of curves look very similar to the ones you would have in the uncharged case. I should note though that we have cheated a little bit here, because what we have actually computed is just the Hawking's early-late matter entanglement entropy, which is this rising curve, and then just essentially the A over 4G as a function of time, which is the curve that descends, and just pick the minimum of these two. So we didn't do the quantum extremal surface calculation for these things. But you can see that these curves look very similar. So that's the main point that I wanted to make here. Okay, so that was it for the first part that I wanted to say. So that was on classical models for charged black hole formation and evaporation. And my second part will be about something completely different. So if you've decoupled, now is a good time to recouple again. And that is about gravity as a gauge theory, lower dimensional gravity as a gauge theory, and the different subtleties that arise there. Well, so as is well known, lower dimensional gravity models are in essence gauge theories, and there's many examples. Well, the most famous example, I guess, is 3D pure gravity at the level of the Lagrangian. It's writable in terms of sum of two Chern-Simons models. Then also in 2 dimensions, generic 2-dimensional dilaton gravity models. So I've written down the action here. They can also be written as a gauge theoretic model, namely as a specific version of what is called the Poisson sigma model. And then if you would specify this generic 2-dimensional dilaton gravity model to a linear dilaton potential, then you can rewrite this in terms of an SL2R BF model, and this is JT gravity again. Now, the main ingredients in all of these different situations is that you use the first order formulation of gravity in terms of the Vielbein and spin connection, and then you embed these degrees of freedom, the Vielbein and spin connection, in the components of the gauge field mu. But there are several layers of complications in making this identification precise and making it work for actual calculations, for actual quantum calculations. And the first of these is that one has non-trivial boundary conditions from the gravity sector or fall-off conditions. For instance, in asymptotically ADS spacetimes, you have these Brown-Henault boundary conditions, so you need to implement those in the gauge theory, of course. Secondly, there exist gauge connections such as mu equals 0 that are perfectly fine from the gauge theory perspective, but they would correspond to singular geometries if you interpret them gravitationally, and you do not want these. So we need to remove these gauge connections that give you non-smooth geometries, both on shell and off shell, and that is a complication from the gauge theory perspective. Another way of phrasing this is that metric invertibility is taken seriously. Thirdly, metrics that differ by large diffeomorphisms, such as on the torus group, they are considered equivalent in gravity, but they are not automatically equivalent in gauge theory. So you need to mod out by this class of diffeomorphisms, and this is not natural to do from the gauge theory perspective. So I will not be talking about this aspect in this talk. And then finally, of course, gravity contains the sum over topologies, which is somewhat ad hoc again from the gauge theory perspective. And I will also not talk about this in this talk. So I will only talk about the first 2 aspects of this identification between gravity as a gauge theory. So the goal is to study these types of questions in detail, and in particular in JT gravity, where we have sufficiently explicit solutions available to see what is going on. And then in the end, I will try to extrapolate these things to the other classes of models that I discussed, the 3D gravity and 2D dilaton gravity models.
So if you do these other things that you said in the previous slide,
This third and fourth one, you mean?
yeah,
and I guess all of the things, like remove the bad, like a mu equals 0. How exact is the match?
Well, then you get the exact gravity answer if you do all of them correctly, right? In JT gravity, we know how to go all the way from gauge theory to, or at least we think we know how to go all the way from gauge theory to gravity. But it depends on how convenient it is to implement these at the gauge theory level again.
That comment I think confuses me. Like, you can put in this ad hoc sum over topologies, and then are there some checks that can be done but haven't been done that fully non-perturbatively matches gravity, or there's?
But you just have to do this sum. It is completely ad hoc. You just have to do it.
Then it matches.
And it matches for each topology. So but it depends whether you find this extremely elegant or not. You have to manipulate the gauge theory a bit in order to make it look like gravity.
Right.
And as I mentioned, these things are not, some of the things are not really natural from the gauge theory perspective. The gauge theory doesn't really want to do these things, at least as far as I understand, and I think that's the current.
Okay. All right. Thank
you. Okay, so I want to be studying these questions in JT gravity, and in the end, I will come back to the 3D, well, I will at least say something about 3D gravity and more generic dilaton models. And for the purposes of this talk, I will only have need of one ingredient that has been computed for JT gravity, which is the disk partition function, which is well known. So this is the answer. So this is the gravitational path integral in JT gravity, restricted to a disk topology with a single boundary of length beta, which one interprets as the inverse temperature. And this is the answer that one gets. And you find the density of states as k times sinh 2 pi k, where the energy variable will be E equals k squared. So that would give you sinh 2 pi square root E. So that's the density of states on the disk. And the only thing that I want to mention about this JT result is its thermodynamic limit, or its saddle, which you can get if you approximate this thing or evaluate it, assuming that the energies are sufficiently large. Then you can approximate the sinh by an exponential, and you find this black hole first law. Square root E is proportional to the temperature, and this indeed matches with the classical black hole. You would write down in ADS2 its mass versus its Hawking temperature. So it is important that this density of states rises exponentially, and I will come back to this in a couple of slides. Okay, so now let's try to discuss the gauge theory implementation of JT gravity as a PSL2R BF model, and let's see what's going on and whether we can make sense of it. So let's first think about compact BF models. So if you study a BF model on a manifold with a boundary, and I will choose the boundary to be along the tau direction, the Euclidean time direction, you can add a boundary term to get the total action that looks like this. So this is the bulk BF model, this is a boundary term, and this is the boundary condition that I implement at the holographic boundary. Now, with these boundary conditions, amplitudes in this compact BF model, they're almost the same as those of 2D Young-Mills theory, which have been determined in the past. And for instance, the disk amplitude in a generic compact group BF model would look like this. So there's a sum over R, where R runs through all of the unitary irreducible representations of the group of interest. Then there's dim R squared, so the dimension of representation you're considering. And then there's e to the minus beta CR, where CR is the quadratic Casimir in that particular representation. So that's the case for the compact groups. Now let's try to generalize this to a non-compact group such as SL2R. And the representations that would appear here in this sum, they are those that would appear mathematically in what is called a Plancherel decomposition. And for SL2R, it is known which representations should appear here, is a continuous principal series representation. So this is a continuous representation where the role of dim R is played by the Plancherel measure, labeled by a continuous number k. And this Plancherel measure for these representations is k times tanh pi k. And there's also discrete lowest and highest weight series representations that are also there. So these are all the representations that you expect just from SL2R group theory. Now, if you go back to the JT disk result that I mentioned on the previous slide, so it was this one, this does not agree with these sets of representations. So first of all, there are no discrete representations. And then secondly, there are continuous ones, but the measure differs. You have a tangent instead of in the group theory case. So what is going on here? Okay, so let's analyze this PSL2R BF action on a disk in a little bit more detail. So here I just retake this BF model with this boundary term. Now, one convenient way to handle this quantum mechanically, so we imagine we have this in a path integral, is that we path integrate over B, this forces F to be 0 or a mu to be, well, one should be able to write a mu as G minus 1 d mu G, at least on the disk. Then you plug that back in the boundary action, and the total action reduces to just the boundary action, which is the particle on a group model. Now, if we implement thermal boundary conditions here, so on our gauge connection, we make it periodic along the thermal circle. But if you demand that the gauge field, well, the tau component of the gauge field is periodic along the thermal circle, this still leaves an ambiguity for this field G, this group element that, well, we have defined in this way, in the sense that G of tau plus beta can be M times G of tau for an arbitrary SL2R monodromy matrix M. This is just because the definition of G, if I give you A, I can always map G to, let's say, S times G, where S is an SL2R matrix, a constant SL2R matrix, and they would cancel out here. So I have this ambiguity, so I have the same ambiguity in this periodicity condition. And well, this would then classify possible defects in our PSL2R BF gauge theory in terms of the different possibilities of this matrix M. And as I just mentioned, this matrix M, because of this ambiguity here of mapping G to S times G, this matrix M is actually equivalent to S times M times S minus 1. So it's the conjugacy class element of SL2R. And the conjugacy classes of SL2R have, of course, been classified. And there's 3 cases. If the trace of M is less than 2, it's called elliptic. And M is always conjugate to a rotation matrix. If the trace of M is bigger than 2, it's hyperbolic. And M is conjugate to something like this. And if the trace is exactly 2, then it's parabolic and can be written in this way.
So is this PSL to our BF theory? Are we treating it as a warm up for the SL to our?
No. PSL means, well, you identify an element with minus
Right.
A, B, C, D, and minus A, minus B, minus C.
So on the previous slide, where
Yeah,
the
I'm slightly careless here during my talk about when I write SL2R and PSL2R.
Right.
Strictly speaking, I should be writing PSL2R everywhere. Right. In any case, it doesn't matter that much since it's just a discrete identification. It's like a factor of 2 if you want.
Gotcha, I see. So I should really think like it's PSL to our BF.
Yes.
equivalent.
I try to be more precise here, but.
Okay, thank you.
Okay, so this is purely in the group theoretical perspective, purely from the PSL to R perspective. This is the classification you get of different possible monodromies on the disk. Now let's go to gravity, because gravity is not, or JT gravity is not actually this. It's very closely related, but not identical. So when we do gravity, we need to implement the gravitational boundary conditions at the boundary of our disk, which is the holographic boundary. So these are just the Brown-Henno boundary conditions. And our gauge field, well, the tau component of our gauge field, well, if I write it in the fundamental representation of SL2R, it should be like this, where there's only a single function here, T of tau, which should be periodic. Now, this T of tau, of course, will have the interpretation of the stress tensor of our model. And then I can just redefine T of tau as the Schwarzschild of something else. So I define F by solving this differential equation given T of tau. And you find immediately that this particle on the group action on the previous slide just reduces to a Schwarzschild action. So this is the one describing JT gravity as I had in the beginning. Now, again, you can do a classification of different monodromies or the analogous thing of different monodromies. And in this case, these Schwarzschild type models, they are classified by the Virasoro coadjuvant orbits. So the coadjuvant orbits of the Virasoro group. So let me mention these. So you have different orbits. And I will restrict to the constant representative orbits because these are the interesting ones. You have the elliptic ones. They are labeled by a number theta, positive number, and they correspond geometrically to having a conical deficit in our disk with an angular periodicity that differs from 2 pi, namely 2 pi theta. And there's an exceptional case where this theta is an integer. And in that case, well, the resulting monodromy would be the unit matrix. The monodromy matrix we had on the previous slide would be the unit matrix. If n equals 1, if theta equals 1, hence this is just a disk partition function, the thing one typically studies, the thermal partition function on the disk, but with n2 or higher, these are replicated manifolds. So this is a special case of the elliptic ones. Then you have the hyperbolic orbits. They are labeled by a positive real number lambda, and they correspond geometrically to a macroscopic tube of a geodesic circumference 2 pi lambda. And there's a parabolic case, which is sort of like the case in between elliptic and hyperbolic, and this corresponds geometrically to a cusp. Now, the thing that I want to point out is that, first of all, these names match with the monodromies on the previous slide. And one directly shows that this time reparameterization f of tau plus beta is m dot f of tau, where m acts by a Möbius transform on f, and with the same f as on the previous slide, and also the same notation. So this theta and lambda, they match with the labels that I used on the previous slide. And so you see that this is almost the same, except that this is a refinement of just the monodromies, because we're keeping track of the winding number in the elliptic case. So this theta, it just ranged between 0 and 1 on the previous slide to cover all of the rotation matrices. But now it can be anything. It can be any real number. So we're keeping track of this winding number as theta goes beyond 1. So that's the only difference here. So now let me make an observation on this difference. If you're giving the gravity results, you can actually go back to the gauge theory results by forgetting about this winding number that existed in these what I call exceptional elliptic sectors by summing over it. So let me show you how that argument goes. So the n wound sector in JT gravity, so when this theta is n, so this is a disk amplitude in JT gravity, one can compute, and this is the answer for it. So it's essentially the same as the disk partition function, except there's an n here. So this k sinh 2 pi nk. That's essentially the only difference. Now let's try to sum these over n, where n runs through all of these, well, all integers. Well, the sum is, if you just stare at it, of course, it's divergent, so we need to regularize it. So let's just add this exponential factor here, where q is the regulator and q is sufficiently large to make the sum converge. Then we get this result, and then in the end, we let q go back to 0 to turn off our regulator. If you do this formal trick, what you find is that the result of summing over all of these different integers n gives you k times tanh pi k. So we started out with k times sinh 2 pi k, from the JT gravity results, and sinh 2 pi nk, and summing over all of them, at least if you trust in this trick that I used, gives you k tanh pi k, which is indeed the correct Blanchet measure of the full SL2R, again, of the actual SL2R instead of the gravitational answer. So what is the interpretation of this? Well, geometrically, the geometries with n equals 2, 3, or higher, they all have conical singularities. They are these replicated manifolds. So if we would demand from our gauge theory that it only corresponds to a smooth geometry, we would have to restrict to n equals 1. That's the only regular one, the only non-singular geometry in this sum over n. And this would effectively cause us to go from the group theory measure, which is k tanh pi k, to k sinh 2 pi k by this restriction to n equals 1. Now, there is a generalization of this that I briefly want to mention, in the sense that this difference between the gravitational measure on the one hand and this group theoretic measure on the other hand, this Blanchet measure of some Lie group G, is way more general. And I think it interplays nicely with black hole physics. So let me show you the results here. So, well, let's be a little bit specific and focus on the SLN-R version. So this is the higher spin version of JT gravity. In that case, one can argue that the gravitational measure that is relevant is essentially k sinh pi k, but you just take a product of these for all positive roots in the algebra. But mathematicians have computed this Blanchet measure for the principal series representations of any real semi-simple Lie group, and you can write it in this way. So it looks very similar, except that now it's k times tanh pi k for every positive root in the algebra. So again, there's a sinh versus tanh mismatch. This is not just true for JT gravity, this is a generic mismatch. So, well, and I think this has a nice interpretation in terms of black hole physics, because if you look at this Blanchet measure, so this group theoretic measure only, that and you try to interpret it the way we want to do it in gravity, so you interpret an energy variable as roughly k squared, well, modulo squared of this vector k, then the large energy asymptote coming from this group theoretic way of looking at this is always polynomial, because this tanh always goes to 1 for large arguments, unlike the sinh, which rises exponentially. So this can never explain the large black hole microstate degeneracy. So these group theoretic things have nothing to do with black holes. Okay, so now let's try to work towards a more general statement on this. So let's consider the gravity path integral in Euclidean signature, and let's do it in the BF variables on some piece of surface that I call sigma, and some interior piece or away from holographic boundaries, or a closed surface if you want. So I imagine doing this path integral over A and B, so these are the BF variables, and I restrict to having just those connections A mu that would correspond geometrically to a smooth metric. So how does one evaluate this path integral? Well, of course, you path integrate over B, you force F to be 0, so you're integrating over all flat connections. And well, let me briefly review some well-known results about these flat connections. They're given by mappings from the fundamental group of the surface to SL2R mod an overall SL2R factor. And one simple way of thinking about this is you need to put an SL2R group element on each non-trivial cycle of the surface, but they have to be compatible with each other, and you need to model by overall conjugation. So as a very simple example, the three-hole sphere. So I put a group element U, V, and W on the three cycles of the three-hole sphere, but there's a relation between them because because they are connected, namely that this W is U times V. So that's what I mean by this. Now, this total modular space of flat connections of SL2R, it famously has one smooth component, one that corresponds with smooth geometries, and this is Teichmüller space, where all the monodromies along all the different cycles of the surface would be in the hyperbolic class. So that would mean that the trace of the monodromy matrix is bigger than 2. So in this case, trace U, trace V, and trace W all have to be bigger than 2 for this to correspond geometrically to a smooth surface. So the question that I now want to ask, given all of this, is there a more systematic way of producing gravity from gauge theory? And the criterion clearly has to be that we need to restrict to smooth geometries or only have hyperbolic monodromies along all of the cycles of our surface. So the trace of all of the monodromy matrices have to be bigger than 2. And then the main question that I want to try to answer here is there a restriction of the algebraic structure of SL2R itself that would automatically reduce to only these hyperbolic monodromy configurations? Is there a way of getting rid of them from the very start? So let's look at, SL2R. So just in the fundamental representation, so ABCD with AD minus BC is 1, then this is smooth or corresponds gravitationally to a smooth geometry if the trace is bigger than 2 or if A plus D is bigger than 2. But this restricting to SL2R matrices with trace bigger than 2, this does not compose well. This property is not preserved under composition. If you have two matrices that satisfy that property, then their product does not automatically satisfy it. But there is a solution. You can actually restrict further to having all 4 entries A, B, C, D to be positive numbers. And in this case, the product of 2 such objects is again contained within the same set, but it doesn't form a group. It's what is called a semigroup. And it's called a positive semigroup because all of the entries are positive. And I call it, mathematicians call it SL plus 2R, and the plus means this positivity. And as I mentioned, this positivity is preserved under composition. And also, very importantly, it's very easy to show that only the hyperbolic monodromies exist in this semigroup. And well, you can quickly check this. So you take the trace A plus D, and then you just use the determinant condition. So D is 1 plus BC divided by A. And then because BC and A are all positive, this is bigger or equal than A plus 1 over A. And if A is positive, A plus 1 over A is always bigger or equal than 2. So only the hyperbolic monodromies exist in the semigroup, only the ones that would correspond to geometric configurations. And one can also prove, but I'm not going to do that here. So one can set up a meaningful representation theory of this semigroup, and one can show that only the principal series irreducible representations exist. The discrete ones do not exist. And if you remember from the beginning, that was one of the mismatches we had between gauge theory and gravity. The second mismatch is that the measure didn't match, but we also had the discrete representations that were also there from group theory, and they're not here in this different object. So now let's look at this measure. Does this thing reproduce the correct measure, yes or no? So what is the measure for the principal series representations here? So I'll first show you a calculation that one can do for full SL2R, for the actual SL2R, and I'll just reproduce the K tanh by K measure. And then I will mention how you need to adjust this to go to this semigroup thing and how you indeed get the correct measure. So this is, well, essentially just a mathematical calculation. So consider representation matrix elements of SL2R in the representation J, where J is minus half plus IK, and then there's 2 representation labels, nu and lambda, and I can write this as this bracket overlap with the group element G. For the group element, I'll use the Gauss-Euler parameterization, so I write it essentially in this way using, well, the typical generators for SL2R, E minus, H, and E plus. And then the states that I have here, we will pick these to be eigenstates of, well, one of them an eigenstate of E plus, the other one of E minus, actually it's E minus dagger, and we will compute this matrix element. So this is a matrix element for which the bra and the ket are eigenstates of a parabolic generator. So it's a parabolic matrix element, but bra and ket are eigenstates of different parabolic generators. So we call it a mixed parabolic matrix element. This also physically is the thing you need to do to implement the gravitational boundary conditions, but that's not the perspective that I want to be doing here. Here I just want to do a pure calculation of this measure, this Plancherel measure in these representations, starting with these matrix elements. So how do you evaluate it? Well, you can just do a coordinate space evaluation by inserting this complete sets of states in an X basis where X is a real number. And in this coordinate basis, these bra and ket wave functions, they're, well, of course, I'm not going to show you the details here, but they're just given by plane waves and some sort of inverted plane waves if you want. And in this coordinate basis, the action of the group element on functions of X is given by this type of, well, this is a well-known formula in representation theory. And then you can in the end just do the X integral and you find this, well, rather complicated looking expression. So let me retake it on the next slide and strip off all the pieces that are not important. So this is essentially this representation matrix element that we had on the previous slide. Notice in particular this cosh pi k factor that appears up front, because that one will be important. Now, once you have representation matrix elements, you can do an orthogonality calculation. So you do an integral over the group manifold, and then the representation matrix times its conjugate. And the result is a product of delta functions, but there's a factor up front. And that factor is 1 over the Plancherel measure. So this is the definition on what this Plancherel measure thing is. So here, again, is just a calculation you can do. And you see that this factor, well, the inverse of this factor is the measure. So it's this one, and you can simplify it just to k tangent by k. So this is reproducing that calculation, reproducing that measure. Now let's make an observation. And I've already written this in a suggestive way. One would instead get the gravitational measure, so not the group theory one, but the gravitational measure, the k sinh 2 pi k, if we could somehow get rid of these cosh pi k factors that would appear here. Now these cosh pi k factors, they just come from here. They were just explicitly there. Now from the detailed formulas, and I'm not going to show you this here, but you have to stare at the formulas long enough. You can see that you can get rid of this cosh pi k here if you can consistently restrict this coordinate space X, instead of being just a real number, being just a positive number. Then you can show that you don't get this cosh pi k and you would get the correct measure. Now, restricting to a positive coordinate space label X is well, you have to check whether this is consistent with this group action, because this group action mapped the point X to the Möbius transformed point X. And that one has to be positive as well for this to be consistent. So if for all positive X, you need this thing to be positive as well, this automatically requires that all 4 entries should be positive. So this restriction to positive X only makes sense for this semigroup construction. So this is at least an indication that this thing has something to do with indeed replacing the tanh with the sinh measure. So is this a coincidence? Because, well, it looked like we did some very subtle things. So can we generalize this to other models and see that the same kinds of sort of mechanisms work there as well? And we checked this for the n=1 supersymmetric case, which is based on OSP 1/2 supergroup. So let me very briefly mention a little bit on how that works. So the OSP 1/2 group, in the fundamental representation, you can write it as this 2/1 dimensional matrix, where you have 9 entries, and all of these are super numbers, but they are restricted by these relations. So the relations themselves obviously don't matter for the purpose of this talk, but I just wanted to show them. And then you have to think on how does one even define something like this positive semigroup? And for that, it's useful to note that any super number can be written as what is called its body plus its soul, where the body doesn't contain any Grassmann components and the soul contains only all of the Grassmann components. And then you can map the positivity of a super number to the positivity of its body. And with that, you can define consistently a positive semigroup by setting again A, B, C, D here. So this SL2R, if you want, sub matrix that's hidden here. Again, demanding all of these to be positive, and that's it. And you can check that the elements in this semigroup, again, only have hyperbolic monodromy. So you can play the same game. You can compute the trace, which gets replaced by a super trace here. And you find that it's always bigger than some number, essentially 2 ± 1, depending on, well, the R or NS sector, but let me not go into that. And one can show that precisely these monodromies geometrically would correspond again to smooth geometry. So this thing is again doing the same kind of, it's doing the same thing. We're restricting to only smooth geometries. And you can show, and well, this was a very long calculation that we did in our paper, that the representation theory of this thing leads to the correct gravitational measure instead of, again, this group theoretical measure one would find for the full OSP 1/2. Instead, you find the one that we indeed know from the n=1 disk result for JT supergravity, or the super Schwarzschild if you want. Okay, so in the last couple of slides, let me try to generalize beyond JT gravity and come back to more generic dilaton gravity models and say something about 3D gravity. So for the most generic dilaton gravity model, we do not know enough, but there's one specific class of models where we can say something, and that is where the dilaton potential is a hyperbolic sine function of the dilaton field. And this has been argued, this class of models, to be equivalent to the non-critical string or to Liouville gravity models. In particular, you can see that, so there's this number b here, this real number b. If you take b to 0, you would Taylor expand the singe, you get back the potential again. So there's a limit that would go back to the things we think we understand better, to the JT gravity results. Now, it has been, or at least we studied this model in these papers, and we have shown that the amplitudes of this model, they look very similar to the ones in JT gravity, except that instead of being governed by an ordinary group, in this case, they're governed by a quantum group framework. And the quantum group itself is a bit subtle. It's called, well, Faddeev's modular double of the Q deformation of SL2R, where the deformation parameter Q is e to the pi IB squared, and this B is the same one as the one that appeared in the dilaton potential. Now, this strange, well, quantum group theoretic object, it has the following properties that, well, you'll recognize if you compare to the JT case again. First of all, its representation theory, it only has the principal series representation, so no discrete representations again. And its measure, its Plancherel measure is singe times singe. So this is very close to the thing we had for this semigroup, and not for full SL2R. And well, it's known that there are two dual ways of thinking about quantum groups. The first is as a deformation of the universal enveloping algebra, which is the standard way of thinking about them, or as a deformation of the space of functions on the group. And if you take that second perspective, then some very suggestive formulas have been written down, mainly by Teschner and collaborators, because this strange object, this modular double here, it corresponds in this, well, in the second formulation, it corresponds to the space L squared SLQ2R plus. So here there's this plus again, and this plus symbol indicates that the entries of this Q deformed SL2R matrix have a positive spectrum. So again, you see positivity of the entries of an SL2R-like object appearing here, but this time in a Q deformed setting. So this naturally embeds the JT positive semigroup story in a larger setting, a setting of Q deformation that has been studied over the past 20 years or so. And well, the last thing that I want to mention here, my last application, is a short comment about 3D pure gravity. So 3D pure gravity, it's well, the analog of the disk diagram is a solid torus amplitude, the solid torus partition function. And it has, again, some sort of spectral density in there, which is precisely the same Q deformed measure that I had on the previous slide. So this singe times singe in each of the two chiral sectors. And I can again make the same observation that I did for JT gravity. We can try to forget the winding number label that appeared in the gravity language by summing over it and making contact with the group theory measure again. So geometrically, this corresponds to summing over these conical or replicated geometries. And the correct spectral density for these conical geometries, well, this is known in 3D gravity, is just, well, singe times singe, but you have this integer n in one of these. These correspond geometrically to having conical defects in 3D gravity. You can sum over these, you need to regularize it, so you play exactly the same game. And then at the end, you set the regulator back to 0. And then you find the dimension of the relevant group. So this is not the gravity results. This is going back from 3D, from the actual 3D gravity results back to the quantum, or sorry, the group that that it corresponds to, which would be a quantum group in this case. So as a check on what this thing actually is, if you take b to 0, you get this s times tanh pi s. So this is some sort of deformation, or if you want a q deformation of the s times tanh pi s, the actual measure you have for ordinary SL2R. And as an additional piece of evidence that this interpretation is correct, you can find this same formula from the modular S matrix you get from characters well, at least if you look at the results from 15 years ago or so, when people looked at the worldsheet torus partition function and string theory for this SL2R of U1 cigar CFT, that was decomposing characters. Those characters, they transform under modular S transforms. And if you stare at that modular S matrix, you can recognize this form appearing there as well. So this thing has actually appeared previously in the literature. Okay, so let me conclude my talk. So, well, JT gravity and related models can be solved in sufficient detail, I think, to be able to learn lessons about how quantum gravity works. And in particular, I talked about two aspects of this during this talk. So firstly, in the first part, I discussed an exactly solvable semi-classical charged black hole evaporation model. And in particular, I focused on analyzing the energetics during the evaporation. And I also embedded this in the supersymmetric evaporating model. And then in the second part of the talk, I argued that the group theoretical description of JT gravity can be suggestively rewritten in terms of this positive semigroup structure that seems to capture only the smooth geometry subsector of the gauge theory. So it was sort of tailored to specifically do that. And then, well, more generically, and I mentioned some things in the end about this. So the exact results we get in 2D JT gravity, they provide for more generic dimensional gravity models, 3D gravity as well. Okay, thank you.
Further questions for Thomas?
Thank you for the very informative talk. So we started by thinking about JT as equivalent to this PSL to our BF theory. Am I supposed to take away that really that was kind of wrong and that it's actually this SL plus?
Well, it's SL2R plus the restriction to the smooth geometries that you somehow need to implement. And you can either try to do this by hand or, and that's at least the perspective that I've been taking, if we use this semigroup thing, it's automatically done for you.
So the idea is that there exists some gauge theory that's like a SL2R plus gauge theory that is perhaps consistent.
Right, right. So doing that at the Lagrangian level is a bit tricky. So the matchings that I showed you, they all work for the amplitudes. So this is kind of, if you restrict to this structure and you just pick the group theoretic ingredients from that structure instead of SL2R, you get all of the correct amplitudes that we have computed in JT gravity using other techniques.
So it seems like that's the right gauge, but I guess, is it the case that we're not yet sure that that itself defines a consistent theory?
Well, we're not entirely sure how to think of this properly in terms of a Lagrangian. I like to think of this more as somehow realizing this restriction in the path integrals, only those configurations that would correspond to geometrically smooth. Yeah, but just trying to think about it classically, yeah, it's confusing. I don't think we fully understood how that works.
I see. Thank you.
Is there some bulk way of thinking about what this restriction to the positive part, to the positive axis means? Like in Chern-Simons theory for ordinary ADS-free, the Chern-Simons fields correspond to the spin connection.
Yeah.
And so then from that point of view, is there a meaning to the positivity? Like maybe something about the Lorentzian picture that you can only go to the future, but not to the past or something?
That would be great, but I don't have a very concrete picture. Yeah.
And I actually have a second question, since I have the microphone. Positivity plays a big role in these modern amplitude computations, like the amplituhedron or the associahedron story. have you thought about, is there a connection between those two stories?
I wouldn't know. Yeah.
Further questions?
Thanks. Could you go back to slide 18, I think it was?
Oh,
Right. So those replica manifolds that you have there, if you, computed Renyi entropies and then, computed a von Neumann entropy using the replica trick, this would be like a von Neumann entropy of what, do you think?
but this would just be the thermal entropy you would
It would
be
be-
computing.
It would just be the thermal entropy.
Right. I
Okay.
think.
Further questions? Not, let's thank Thomas again.